Okay, Euclid's proof of infinite primes is going to be a proof by contradiction. So if we make a proof by contradiction, we first need to make an assumption. If we contradict this assumption, then we know the opposite is true, which is primes are infinite. We're going to assume primes are finite. So prime 1, 2, 3, 5, keep going all the way till the last prime, and it's finite. If we contradict this, then we know primes are infinite. What we're going to do first is just assume primes are finite, but we're just going to assume the list is only too long, which we know is not true. We have this 5 and 7, and we can keep going. But we're going to start there. We're going to take P1 times P2 plus 1. So we all know that this is 7, 2 times 3, right? Prime 1 times prime 2, plus 1 is 7. So we already know it's prime, but we're going to leave it in a more general form. So this could be prime, or it could be composite. Let's say it's prime. P1 times P2 plus 1 is greater than P1, and it's greater than P2. So if this is a prime and it's greater than P1, well then it's not P1 and it's a prime. Okay, so we're assuming that this is a prime. If this is a prime and it's greater than P2, then it's a prime, but it's not P2. So we have a contradiction. We must have a new prime that's greater than the complete list of primes. The list is only too long. So we have a contradiction. So there must be another prime other than just those two. Okay. We're going to assume maybe this number is composite, which means you can break it apart. So 15, 3, and 5. Okay. So if P1 times P2 plus 1 is composite, you must be able to divide it. So let's look at this number first. P1 times P2, that's 6. 6 divides 3? Yeah. Answer's 2. Does 6 divide 2? Yes. Answer's 3. So I'm going to show you a new way to divide. And Euclid did not know algebra because he was around before algebra was invented. So we're going to divide this 6 by 3. So this is 6 divided by 3. We can see that it's 2. It's 3 boxes, 3 boxes. So we get 2 of these. 6 divided by 3 is 2. Here, we can see 6 divided by 2 is 3. So 2 boxes. 2 boxes. 2 boxes. So we can see that this divides easily. But the problem is when we add 1. However long this is, if we just have multiplication, then we could easily find factors. We could easily find numbers that divide this number, like 2 and 3. But when we add another box, this is 7, we say 2 does not divide 7. And 3 does not divide 7 because of the plus 1. So no matter what happens, we can't divide it. So we say P1 does not divide this number, and P2 does not divide this number. So, if it's composite, it must be made out of primes. But it's not made out of any primes in the complete list, right? Because this is supposedly a complete list. P1 and P2, that's it. But none of the primes in the list divide it. So let's say it is a composite, so it is made out of primes. So let's just say Py and Px divide it. Well, we know that P1 does not divide it and P2 does not divide it, but if Px and Py divide it, those are two extra primes in our list that need to be added to this list. So this is not a complete list, contradiction. Let me just recap. P1 times P2 plus 1 could be prime. But it's greater than all the other primes that exist in the complete list. Because that's our assumption, right? That there's a complete list of primes and that complete list is finite. So we arrive at a contradiction. It's greater, it's a prime, right? Assume it's a prime, but it's greater than this one, so it's not that prime. And it's greater than this one, it's not that prime. So it's a new prime that needs to be added to the list. It's not a complete list. Okay, so if it's composite, well then it's made out of primes. But this number is not made out of this prime, and it's not made out of this prime. So it does break apart because it's composite, so there must be two new primes that need to be added to this list. So with this logic, we can continue. Instead of just making a list that's too long, which is just has two elements, we can make a list that has however many we want. So we have the list of primes. We're going to assume that this is a complete list. We're going to take them. We're going to multiply them all by each other. And then we're going to add 1. We're going to assume that number is prime. If that number is prime, P1 times P2 times P3, etc., all the way to Pn is surely greater than P1. It's surely greater than P2. It's surely greater than P3. Keep going all the way to Pn. It's greater than anything in this list. So if it's a prime, but this number, plus 1. If this is a prime, and it's greater than all the primes in the so-called complete list, then we have a contradiction. The list is not complete. Okay, so this number here could be composite. That's the only two options we have. It could be prime or composite. If it's composite, P1 times P2 what divides it? Well, does P1 divide this number? No, because of the plus 1 like we learned earlier. No. Does P2? No. P2 does not divide this number. P3 does not divide this number all the way to Pn. Pn does not divide this number either because of the plus 1. The same logic applies to all of them. So this number again is made out of two primes that are not in this list because a composite number is made out of primes. So we just say, okay, Px and a py. We don't know what these numbers are. So P1 does not divide this. P2 all the way to Pn does not divide this. But it's a composite number, so it must be divided by something. It must be able to be broken apart into 2 primes. Or more. 2 primes or more. So maybe more than that. But we won't get into that. Well then, we have 2 primes that need to be added to the list. But I thought that this was a complete list. This is all the primes. All the primes are finite. Well, no, we're missing more. So this logic always applies, and we get a contradiction here. So if this number is prime, then we arrive at a contradiction through our assumption. If this number is composite, well, then we arrive at a contradiction. So no matter what, we arrive at a contradiction, contradicting our assumption that primes are finite, so therefore primes are infinite.